happy to have you joining us today. Thank you.
Thank you. Hey guys. Are you able to hear me? Yeah. Okay, so I'm Sharada Yeluri from Juniper Networks. So this talk is going to be on networking for AI. Our previous speaker, Yun, she talked about how to use AI to optimize the networks, like, improve the security and modeling and digital twins and everything. So this is the opposite of it. This is about how to use the network to optimize the AI itself, like, optimize the training as well as the inference workloads. So I'll go over those topics, and the agenda is like this. First, we'll talk about what is backend fabric and what are the training workloads and the role of network, and especially the Ethernet switches in training as well as inference. And we talk about the network requirements, what is needed in these switches. And lastly, something that many of you must have already heard, that's the UEC, Ultra Ethernet Consortium. I'll talk a little bit more about that as well. And finally end it with inference workloads and the role of network in inference. Okay. So first, talking about the large language models and Gen AI workloads, pretty much all of you know by now, what these are. And the chart that's on the top right side, many of you must have seen it. All it says is that there was a strong belief in the beginning that the larger the model and the larger the data set, the performance of the AI would be very close to human when it comes to natural language processing as well as computer vision. So since then, the models have been growing, and you see the second inflection point around 4 or 5 years ago with the transformer models. Those are the ones that are used in the large language training, and they were growing even more faster pace. And we see that the GPT models coming from OpenAI, they were going 10x with every release. And recently, we have also seen in the last couple of years that Meta released the models that are much smaller than what GPT has. And 2 weeks ago, that's why it was not captured in this table, is the DeepSeek release from China. And that's still relatively a large model. It's about 700 billion parameter model. So there are no clear trends when it comes to the size of the models, and between a different family, when it comes to some foundational models from OpenAI, they continue to grow. There are other models from Meta as well as from other companies where they are starting at a smaller scale than OpenAI, but they also continue to grow. Even if you take a DeepSeek model, right? So they use 2,000 GPUs to train in 2 months. And at later time, if they want to increase the pace of training, let's say you want to finish the training in 1 week, the number of GPUs that you need still scales. It goes to 2,000 times 8 or something around 10. You still need thousands of GPUs, some 16,000 to 20,000 GPUs. So, and the other thing about the models is that there is a trend that's going on where even if the models get simpler during training because they have less number of parameters, and the reason they are able to perform well is because most of the computation is now going to inference. With inference time compute, agentic workflows, and test time training, and all of that, right? So the need for the GPUs is kind of shifting. Even if you don't need that many GPUs for training, then you're pretty much moving that necessity to inference. So with all of that, the role of network continues to be pretty critical when it comes to whether AI training or inference, because all of these models, they're not going to fit in a single GPU. So you would need, whenever you have to distribute these models across thousands of GPUs, you need to connect them through a network. So that's what is the backend fabric. And when the model is distributed, so the parameters and the intermediate states, they're all stored in the GPU memories. And these are all during the training as well as during the inference, they're exchanging tons of state. So the role of network in terms of making sure that the state is exchanged more optimally is more and more it's continued to be more important. So the backend fabric, it's like, is a very high level description of what the backend fabric is. As you see, this is connecting the servers that contain the GPUs, and that it's kind of disjoint from the front end, which is all like, we all know in the data centers. But the topology is kind of similar, like, mostly it's using fat tree class topology. And when there are so many GPUs that are talking to each other, there are multiple ways of partitioning the model. And the first one is the tensor parallelism, and which is mostly used for like, partitioning the matrix multiplications that are spread across the GPUs. And the ones like on the top that we show, like, the parallel GPUs in each pipeline stage, those are the tensor parallel GPUs. Then there is a pipeline parallelism where the model is partitioned across GPUs at the boundary of a group of layers. Then the last one is the data parallelism, where you have many model copies and each one is used using a mini batch to train its model. Then afterwards there is like, some kind of convergence that happens between the gradients. So I'll go a little bit more about the data parallelism. So what happens here is each model copy goes through its iteration of training. And to get the gradients for parameters, the parameter is the weights of the computational elements in the neural networks. And at the end of the iteration of training, you have like, gradients for every single parameter across every single model copy. So for each parameter, all the gradients need to be added across the model copies. So that's where the broadcast happens. The gradients are all aggregated. Then the aggregated gradients are broadcast to all the model copies. So the model copies can adjust the parameters. Then they start the next iteration. So that's what happens in the data parallelism. So so now let's talk about the kind of traffic patterns that you see in each one of these, like, different ways of like, partitioning the model. In tensor parallel traffic, if you recall, it's mostly for the matrix multiplications, all the partial matrix multiplications that are happening and the results that are exchanged between the tensor parallel GPUs. These are very high bandwidth. Mostly the frameworks, the deep learning and LLM frameworks, they try to keep it within the server. The reason for it is inside the server, mostly the GPUs are connected with very high bandwidth links. In case of like, NVIDIA GPU servers, you have this NV links that are connected through the NV switch, and they have almost 9 times the bandwidth than the connection that's going outside to connect to the external fabric. So because matrix multiplication carries like, a lot of data, and it happens pretty often within a single layer of network, the frameworks are always keeping this kind of traffic within the server. Then the second kind of traffic is the pipeline parallel traffic, and mostly, I mean, the trend is to use a rail optimized design. What it means by rail optimized design is, as you can see here, right, you have a many number of servers with their GPUs inside. Then you also have rail switches. The nth GPU, for example, the first GPU in each server will connect to the first rail switch. So that way, like, we are able to partition the traffic nicely and use the bandwidth between the servers and the rail switches more efficiently. And in the rail optimized design, anytime a GPU needs to talk to another GPU that is not on the same rail, first they use the NV link to talk to the corresponding GPU on the same rank. Then the GPU in the rank in that server will talk to the other GPU in the same rank using the rail switch. So then the third one is the data parallel traffic. So the data parallel traffic, like discussed before, it is for gradient aggregation. So after each iteration of training, every model copy is sitting with a gradient, and for every single parameter that it has, right? So at the end of the training, all these parameters have to be aggregated. So for simplicity, we have shown a diagram like this. So you have, let's say, in each model copy, you have like NM GPUs. So the GPUs in the same rank, for example, the GPU 1. So all those parameters are aggregated using a gradient aggregation thread. Like that, if you have 100 GPUs in a model copy, then you have 100 gradient aggregation threads that are happening. There are multiple ways of doing gradient aggregation. If the network bandwidth is not a concern, we could use like a hierarchical tree aggregation. Or if you want to reduce the bandwidth, there are techniques like ring all reduce, where each GPU is sending its set of parameters to the next GPU in the thread, and the next one does the accumulation of the parameters and sends the partial accumulated result to the third one. Like that, we could do that. And at the end, you have the final sum, and the sum can be again propagated back in the ring fashion. So there are multiple ways the gradient aggregation can happen, and the frameworks pick the aggregation based on the network topology. So then there is another kind of data parallel traffic that's used for the model parameter sharding. What it means is that when you are sitting with so many model copies, and each model copy has to store all the parameters that are needed for the training, then we are kind of replicating the same thing across all the model copies and not using the GPU memories very efficiently. So there is one way of reducing the memory footprint, that is to distribute the parameters across the model copies. And just before the training iteration, whenever a GPU rank needs its set of parameters, it is reading from all the other model copies and putting them all together and doing its part of the training iteration. So by doing that, we could reduce the footprint of memory in each GPU, but at the same time, it's increasing a lot of traffic in the data parallel traffic, because for every iteration, before the GPU has to use do computations on that part of the model, it has to fetch the parameters from all the GPUs. And so this is like a balance that we pick based on the network topology as well as the performance requirements of the training. So I talked about all these different network traffics during the AI training, right? The network plays a very critical role in the job completion time, and we all know that there are many iterations in the training, and like I talked about it before, the gradient aggregation is a synchronization point and for next iteration. And even if there is a single GPU that's choking, or if there is a single link or single network switch that is congested, then it's going to affect all the GPUs, all the training performance, because the next iteration cannot start until the current iteration is complete. So that's why the tail latency is extremely important for the job completion time. A single or few choke points can bring the entire training down. So there is, so how do you build this network, right? Originally, about a couple of years back, or even even the last year, there's been some debate on whether to use the Ethernet or InfiniBand switch for the networking. In my opinion, the debate doesn't exist anymore. Ethernet is the way to go. And because of the large ecosystem Ethernet has, and also it's filled pretty much all the gap between the performance of the InfiniBand versus Ethernet. Before going into more details, let me talk about how the traffic goes in the network. So when you do the GPU training or even GPU inference, the traffic between the GPUs, we want it to be more efficient when it is transferring information between the GPUs. So we don't want to go through the system memory in the CPU. So that's where the RDMA, that is the remote direct memory access, is used for transmission. But unfortunately, the RDMA protocol, when it was invented, it was mostly for the storage networks. So they did not, there are very strict requirements. So they don't allow any packet drops. Anytime there is it's a sequence number based transmission. So they require very strict ordering of all the writes that are going between the sender and the receiver. And anytime there is a packet drop, like a missing sequence number, it could trigger a go back N retransmission or selective retransmission. Both InfiniBand and Ethernet both support RDMA. InfiniBand supports it natively, and Ethernet also supports it over RoCEv2 over IP, Ethernet and IP UDP. And both are efficient when it comes to that, because they don't involve the host GPU when doing the transmission between the GPUs. Okay, so then let's talk about, so we talked about the traffic patterns, and I also talked about what's the protocol that's used when transmitting the traffic between the GPUs in the network. And then coming to the network topology itself, how do we build the networks, backend networks? So there is always a debate whether you want to go with the modular system or the fixed form factor system. And modular systems have their own advantages. For example, they give you lot more density, and so you have fewer switches in the network, and it's simpler to connect and simpler to maintain. And when the network is completely loaded, so it's more power and cost efficient building it with the modular systems, and they have very superior non-blocking capacity. What it means is that in a chassis, containing the congestion and making sure that you don't have in-cast problems, that's the responsibility of the vendor. So they take care of it by giving very efficient VOQ. Most of the times you find it VOQ or virtual output queue mechanisms that are given between the ports, so they don't have in-cast congestion issues. So that's why they have superior non-blocking connectivity between the ports. The other thing about the modular systems is that they come with deep buffers, so they can absorb transient congestions. And finally, most of these systems come with 1000 ports or 1024 ports or 400 gig. And if you look at most of the open source models like Llama and all those, they require less than 1000 GPUs for training, and they require even much lesser GPUs for inference. So for smaller models, there is a very good possibility that a single modular system can also do the training for the model. So now the case for the standalone systems, and this is mostly the blast radius is small. So anytime you have a switch that goes down, you are not impacting way too many GPUs. And in the same sense, adding redundancy is not expensive when the switches are small and they are not very costly to purchase and maintain. And the third thing about the standalone systems is that they have shallow buffers, lot of them, and these shallow buffer standalone systems are catching up in the density, in the port density. For example, 51.2 terabits per second systems are in the market with 800 gig ports, and 112.4 terabits per second is in the work. I think they'll be released next year or so. So the density advantage is kind of the gap is filling very fast between the modular and fixed form factor switches. And there is also a thinking that if you have a shallow buffer switch, and if there is a congestion, the congestion can be notified to the endpoint much faster. So that way the endpoints can react to the congestion control quicker, and that way you avoid the congestion in the network instead of letting the packets go and sit in the deep buffer. So there are pros and cons. So there is always a debate on what is the right way to go. But hybrid systems with modular chassis in the spine of the fat tree, that clause topology, and with the shallow buffers in the leaf, that is also a very popular choice. That's a balance between how many switches you can have, how do you control the congestion, versus how much redundancy you can add in the leaf level. So it's a good balance, and many hyperscalers, they also prefer this kind of approach, where it's a mix and match of the modular versus the single standalone systems. So now going to the network topology, we could build a topology that's completely non-blocking, and that means your uplink and downlink bandwidths, they match. And it is preferable when you're building a cluster that is used for diverse training, you're not just doing LLM training, but you are doing all kind of training of the models. But the only thing is, if you want to build networks with hundreds of thousands of GPUs, and this is pretty expensive to scale. I mean, it exponentially increases. And the second topology is to create some kind of a oversubscription between the leaf and spine. And if you remember before, lot of times when the frameworks are like partitioning the GPU workload, they keep the tensor parallel traffic inside the server, pipeline parallel traffic in the rail optimized, which is the box inside in the rail optimized connection, in the data parallel traffic, which is the gradient aggregation, and also some parameter exchange if you are doing the parameter sharding, that goes between the leaf and spine. So if the parameter aggregation can be metered out by using ring all reduce or some other algorithms, we could reduce the bandwidth of the traffic that's going between the leaf and spine. And there is a way to, if you reduce the bandwidth, then you could also create some kind of an oversubscription. So by doing that, the number of switches can be saved in the network. It can have 50% fewer switches, and overall it can be less expensive to maintain. But there is a downside, especially if the network is used for parameter sharding as well, then the traffic is increasing, and then you won't be able to do at a full performance with kind of this topology. And the third one is the rail optimized one that we talked before. So if the network is small and your models only need less number of GPUs to train, you could also build a network with only rail switches without the spine switches. So coming to the network switch requirements and uncongested fabric, these are all the good things to have, because we talked about how a fabric congestion in the network can slow down the entire training. So it's very important. While everything that's listed here is important, the most important things are having a very high link utilization, lossless transmission because of the fact that we are using this RTMA protocol, and uncongested fabric. Those are extremely critical when building the network with Ethernet switches, right? So the congestion, what is the source of congestion in this backend fabric, right? Most of the times when the GPUs are exchanging information, they don't have these are very high bandwidth flows. They don't have that many flows between the GPUs, so the entropy is very low. So if you use the standard techniques that Ethernet uses, like ECMP load balancing, it could create too much of uneven link distribution, because many of the flows are not mostly mapped to a few links, and that causes this congestion between leaf and spine. Then there is another cause of congestion that's called incast congestion that happens between spine to leaf as well as from leaf to the switch. Incast happens where more number of senders want to go to a less number of receivers. So then, for example, you have that leaf that's on the right side. If there is more traffic headed towards that leaf, because all of them are going to the GPUs that are connected to the leaf downlink, than that spine to leaf link can handle, then you are creating an incast. Similarly, if there is a lot more traffic trying to go towards the GPU than that link between the leaf and the GPU can handle, then you are causing incast. So incast can happen because of the transient traffic scenarios when you are in the training, because there could be multiple training workloads that are happening in parallel, and even there could be multiple parallel threads that are happening when you are doing gradient aggregation or pipeline parallel traffic. So incast could create scenarios where things can start back pressuring, and soon you would see that spine buffers are filling up or leaf buffers are filling up, and then we could potentially see a packet drop. So there are many ways to improve the congestion. One of the things that have been discussed a lot last year is the packet spray. So what it means is that instead of doing ECMP load balancing at a flow level, where every flow picks a link and then goes through that link, you could do that load balancing at the packet level, and packets can be sprayed across the links. But the only problem is that they're all going to come at the receiver out of order, and RDMA cannot handle out of order reception. So that means the NIC that's sitting in between has to put the packets back in order based on the sequence number. And it puts an extra burden on the NIC. Not all the NICs support this. And even in NVIDIA side, they only put very limited support, especially if you are using an Ethernet switch to connect to the NVIDIA NICs. So that's not an option anymore, especially with the latest NVIDIA NICs. Then the second thing is the dynamic load balancing. So when the links are heavily utilized, you switch to the, the flows can switch between the links. But we want to do that only when there is a gap between the flows. So that way you do not cause reorder at the receiver. And that way, the packets can see in order. But the problem with this is it doesn't take effect immediately because we are waiting for a gap before you do the switching, right? And the next problem that needs to be solved in the network is the incast. So like I said, incast happens when there are more things that are trying to go to a receiver than what it can handle. And one way to solve the incast is to use a distributed schedule fabric. At a very high level, think of it as a fabric that's happening that is already exist inside the modular chassis. If you look at a modular chassis with the line cards and the fabric cards, how they communicate with each other internal, that's like it's always a vendor specific protocol, and it's using some kind of a request and grant handshake so that there is no incast at the output port, right? So the same concept can be extended and do the request and grant handshake between the leaf switches so that you solve the incast problem. The only problem with this kind of things is that whatever a protocol we come up with, it's going to be like a vendor specific protocol. So there is a danger that there will be a vendor lock-in, and it's not easy for interoperability. So you are going to be limited to using a specific vendor's set of leaf and spine switches. So other thought that's going on is, instead of doing this handshake between the leaf switches, you could do the handshake between the NICs as well. They can also the host as well can do the handshake and get the packets go with this request and grant handshake. That can be done in the hardware in the NIC or in the host. And many other congestion control algorithms can also solve incast, like the ECN mechanism that we all know, that we use in the Ethernet. The switches can inform the endpoints that there is a congestion, and the endpoints can reduce the traffic rate in reaction to the congestion. So that way you could also solve the incast problem. And ECN marking usually has only a single bit. There are other ECN marking protocols other congestion marking protocols like CSIG that was open sourced by Google, as well as INT and IFA, which carry more information inside the packet. So you are able to modulate the traffic a lot more efficiently and lot more proactively. So those are also can be used. So as you can see, there are many protocols or many methods to solve the congestion. We talked about packet spray, flowlet based dynamic load balancing. We talked about the distributed schedule fabric, ECN, and different mechanisms for solving the congestion. The problem here is that not every switch, even though all the there are many Ethernet vendors and then they all build switches, not everyone will have every one of these features. So there is no true interoperability if you go this way, where everybody picks their own way of solving the problems. And also we have seen that the RDMA itself, using that for the GPU to GPU communication is adding lot more constraints to the network, that the network has always have to deliver the packets in order. So in order to improve all of that, many of the Ethernet switch vendors as well as the hyperscalers, they all got together and started this consortium called Ultra Ethernet Consortium. The goal of the consortium is to come up with an open set of protocols that can improve the backend fabric and make it truly interoperable. So that means if you have a UEC compliant switches from 3 vendors or 4 vendors, you should be able to mix and match without worrying about whether a vendor will support one feature or not. So that was the main goal. And this Ultra Ethernet Consortium, I think it was formed 1.5 years ago or so. And like I said, the goal is to deliver open, interoperable, and high performance communication stack. And HPE and Juniper and many others are members of this consortium. and they are solving all the issues that we have, like the flexible delivery order is something they want to add. And so they have come up with a new transport protocol that doesn't put all these strict ordering requirements when transmitting the packets, when doing the GPU to GPU transmission. And there are modern congestion control protocols, and they also have the specifications for security, stability, and all of that stuff. So the main things that are happening in the UEC are in physical link layer as well as the transport and software layers. On the link layer, which is at the layer 1 and layer 2, so you have they are introducing something called link level retry. This is similar to what we see in these PCIe interfaces, that anytime you have an error, retransmission happens. Increasingly it's needed because as this GPU scales increase, we do want there are much more fatter pipes that are transferring the data between the GPUs. We will be using 200 gig links going forward. So the error rates are high. So link level retry is there to reduce the error rate between the GPUs. And they are also trying to improve the PFC by having credit based flow control. And there are other things like improving the packet rate by compressing the L2, L3. And those are mostly targeted towards the HPC applications because the UEC consortium is addressing both HPC as well as the AI. On the transport and the software side, they are doing lip fabric extensions. On the transport side, the main innovation is happening here. So we have a new transport protocol that has a lot more message passing semantics between the GPUs. And it puts very less requirements on the switch in terms of maintaining the order of the packets. Okay? And what we are doing for UEC, Juniper, we have the Express family of switches that we use in PTX routers. So we are going to incorporate, or we are incorporating all the UEC features in Express 6. And congestion control, whether it's in ECN or packet trimming and CSIG, these are some of the mechanisms that UEC is proposing. All of that we will have. And link level retry also we are planning to support on the Juniper switches. And with that we will talk, I'm completing the training part of the GPU as well as the UEC. Now let me talk a little bit about the inference as well, because inference is gaining a lot more momentum these days with a lot of things happening on the inference side, things moving from training to inference. So what is LLM inference, right? So you have a trained model, and all that model can do is you give a string of text or a string of an input. It will predict the next token. It doesn't predict the entire output. It's always predicting a next token. Then you take that next token and merge it, put it together with the input and give it back to the trained model again. Then it will predict the next token and so on. So here, if you see the illustration here, right? If you ask an inference model, is Goa a fruit, right? So it has to go through the many iterations before it tells you the answer, yes it is, right? The first time all the tokens are fed in the iteration 1, it gives the first answer yes, right? Then after you take all of those tokens and feed it again, and the second token comes and the third token comes, like that until the end of the sequence reaches, right? So the inference has two processes. The prefill phase is the first one where the first token is generated, where it takes the entire input context, whatever input that you're feeding, and it is computationally intensive, and it comes up with the first output token. After that, the state of the inference, which includes the entire input tokens and the first token, is stored in something called KV cache, key value pair cache. So it can be read back in the second iteration, and it is going to give the second token. And like that, then again you store it in the KV cache and read it back and so on. So the first iteration, which is called the prefill phase, is extremely compute intensive. It depends upon the size of the input that you are giving. After that, every iteration until you go to the end of the iteration, they are memory bound, because the state is stored in the KV cache and the state is read out of the KV cache. So it all depends upon the bandwidth of the memory and how quickly we can read from the memory. That kind of defines how fast the inference can go. And also to amortize the memory cache, like, people, like, all the inference servers, they try to batch many users. So anytime that you are reading a memory output, you are able to, like, use it for parameters, not the KV cache. KV cache is specific to the user. So the parameters, whenever you read, they are going to be, like, they can be used across multiple users. So that can be done too. So when it comes to GPU scale for inference, we talked about in training, you need hundreds of thousands of GPUs, right? Compared to that, inference has much less requirements when it comes to training. And you must have seen all this, like, news last week, like, DeepSeek model needs like just a single server for inference. That's what even NVIDIA proved it, like, they used a single H800 server, like, with 8 GPUs, and they were able to, like, put the model of the DeepSeek and able to do the inference. It's the same for all the Llama models too, for Meta and everything. A single server or a few number of servers can fit the model, and it doesn't need, even if you need thousands of GPUs because you have many users that are using the inference, you still need a network. But the good thing about the network is that these users are not working in lockstep, like the training, right? In the training, we said, like, you have the single iteration. After the iteration finishes, only you can go to the next iteration. So those kind of requirements are not there in the inference. So the network requirements are little bit less stringent when it comes to inference. But as the inference demand grows exponentially, because the models are becoming more and more cost efficient and they are more readily available for the companies, then the demand for the network also grows for inference. So it's always, the network is always playing a role, whether it is training or whether it comes to inference. The second thing about the inference is that, as you have seen, the shift now, many models are they're all supporting something called agentic workflows. And so that means, like, you give a task to the a inference server, it breaks it into many subtasks, and each subtask is doing its own inference. Then they also call something called inference time compute. That's kind of like, at a very high level, let's say you have a task, a subtask, like, you could do, like, do the inference on multiple parallel, in parallel models, and take the results and then do some voting to pick what is the most optimal result or something like that. Then there is a test time training. So all of that are increasing the need. Even though you need a single server to do a single inference, you will probably end up using tens of servers to do all these agentic workflows, inference time compute, and the test time training and everything. And the other thing about the inference is hosting models across the network. Like, instead of putting it in the just the cloud, at the hyperscale, like, putting it at the edge locations, and sometimes even the laptops can also have, like, inference model that reduces the latency and makes the user experience, like, much better. So that's all about the inference. Finally, like, I just wanted to conclude this by saying that there's a continued demand for GPU clusters, whether it's training, inference, or a mix. So the same network that you build for training can be interchangeably used for inference as well. And Ethernet and IP fabric will be a dominant fabric. There's no debate about it. I mean, the war between Ethernet and InfiniBand is long gone. Ethernet is a clear winner. And UEC Consortium is there to make Ethernet the superior choice for both training and inference, with all this high interoperability that it's adding to both NICs and the Ethernet switches. With that, I think I'll conclude my presentation. And do you guys have any questions?
Okay, the usual poke for anybody putting in a remote question, and the back microphone, please. We only have a few minutes.
Randy Zhang from Cisco. Sharada, thank you for sharing the insights. I have a question about some of the vendors, they're looking at, instead of the UEC type of consortium kind of a protocol, they're looking at some type of overlay on top of the Ethernet, right? Breaking the Ethernet packets into cells and send the cells. You can have no congestion, schedule the cells. On the other end, you reassemble the cells back into the packets. What is your thoughts on that?
So I think I covered that in one of the slides. That's why I call it like a distributed schedule fabric. So that's like using the, whatever mechanism that was used within the modular chassis, you kind of replicate that across the network between the leaf and spine. It has pros and cons. It's very good at solving the incast for sure, because there's a very tight scheduling. But the problem is when your networks get much larger, and it would add a lot more burden on the leaf switches, because your buffering requirements will increase on the leaf, right? So we had some kind of analysis that was done, and we see that at some point it becomes it adds so much burden on the leaf that leaf switches starts becoming a lot more expensive, or the scale of the network has to get smaller. So it would, in my opinion, it would have more problems in large networks, right? And the second thing is it's a very vendor specific. UEC is not trying to come up with any protocol for that. So you are locked into a vendor, whether you go with Broadcom or Cisco or something that's the only thing you can use.
Definitely, it's vendor specific. Thank you.
Yeah.
Okay, thank you very much.
Thank you.